To write a quadratic equation for a line that intersects 3 points, you will need to make a system of 3 equations by replacing the x and y values in the equation, because that's what it gives you. Okay, so remember, we have this format here, y equals ax squared plus bx plus c, which we love so much. But in the ordered pairs, they're going to give us 3 ordered pairs. 1, 2, 3, something like this. And then you got x and y values throughout. Okay, this is saying that what you got to do is you take those x's and replace it with whatever x value is given, and then whatever y value is given, but you got to do it 3 times. And this will create a system of equations with 3 variables that are now a, b, and c, not x's and y's. And as funky as that sounds, it is so fun.
James Brown.
Almost, yeah, like James Brown. So write the quadratic equation for the line going through the 3 points, negative 217, 1, 5, and 429. Now, I need 3 equations out of this, 1 for each ordered pair, by the way. And so we got to remember the standard form for our quadratics. Now, the first one, I'm going to make this equation red, because this is for the first ordered pair where the x is negative 2 and the y is 17. So, for y equals ax squared plus bx plus c, I know the y value is 17 right now, and I know that the x values are negative 2. Okay, so writing this out, I've got 17 equals a times negative 2 squared plus b times negative 2 plus c. And to simplify this then, would become 17 equals negative 2 times negative 2 would be 4, so that's 4a. And then, well, negative 2 b's, and then plus the c. Okay? That's my first equation. But I've got to do it with all 3 ordered pairs. So we get the pleasure of doing this all over again, but with the new ordered pair. So let's do the 1, 5. I'll do this one in purple because it's just my next color. But again, it's the same idea. The y value here is 5. The corresponding x values are just 1s, and that's nice, because 1s is pretty easy to work with. But now I get 5 equals a times 1 squared plus b times 1 plus c, and this just ends up being 5 equals, you can make it 1a if you'd like. In fact, I will show the 1 because I think it's going to make things easier. And then even the coefficient of b, I'll show that as 1 as well. Okay, so this in purple, 5 equals 1a plus 1b plus c is my second equation. But I need my third equation to make it triple the fun. So the third ordered pair, the x is 4, the y is 29. So I've got a 29, and then again, all my x's are replaced with 4s. So I've got 29 equals a times 4 squared plus b times 4 plus c. And we'll simplify this. So 29 then equals 4 times 4 would be 16a. And then plus 4b, yep. There's my b plus 4b's. And then plus the c. This is my third equation. Now, we probably are not used to seeing the equations written like this. So what I'm going to do is I'm going to restack these so that it looks more like a system of equations. There's my first equation that we found, the second one. It doesn't matter which order you find them in, by the way, just as long as hopefully you find them. And then, of course, we have the green one here as well. So this is my system of equations that will help me to solve for the a, b, and c, which is the original quadratic for all 3 of these ordered pairs, meaning that once we find the a, b, and c for our quadratic, you could have replaced these values into that quadratic, the same quadratic, and you get true statements out of it, if that matters to you. But my system of 3 equations, if you have experience solving these with matrices, feel free to use that. But since we haven't in this class, I'm not going to, as much as you want me to. So I would probably look at these 3 right here, and I'd say, you know what, I can get rid of those c's pretty easily. Okay. In fact, I could probably get rid of the a's or b's pretty easily just because of this equation right here in the middle. but I'm going to leave it up to you guys. What do you guys want me to eliminate first? Let us eliminate the C's then, because it has been declared. All right, so I'm going to take the first two equations. We have chosen to eliminate the C's. We'll see how that goes. And from this, I know right now the C, I got my C's. Their coefficients, by the way, are 1s. But I need them to be opposites. One's positive, I would like for one to be positive and one to be negative. And so to do that, I'm just going to change the signs of the second equation. Of course, that'd be multiplying by -1. The reason why I'm doing that is because when I add these two together, now, in these columns, which match, let's start on the left. I got 17 minus 5, which is 12, which equals 4a's minus or plus -1a's, which would be 3a's. And then I've got -2b's plus -1b's, which would be -3b's. And then the 1c, and now it's minus 1c, has zeroed itself out as planned. Yeah, so multiplying all these values by -1 is what changed those into minuses for us, essentially minuses. And that did eliminate the c's, because before they were the same coefficient, +1. I need them to be opposites. So +1 and -1, and that does eliminate them. And this is it's a fairly decent looking equation. 12 equals 3a minus 3b. If you wanted to simplify that by dividing everything by 3, you could. But I'm gonna avoid that because that may not be so obvious to everyone. Yeah, now I've got to do it again, and I'm just going to use the bottom two equation. I used the top two first, so I'm going to use the bottom two now to eliminate, again, the C. And by doing this, I will then have a new system, but it will only be in two variables. So let's take a look at that. Now, again, I have the same problem. The C's have the same coefficient of +1.
Would this be the order you'd have?
This goes back to, I think it was model 2, but yeah, I chose the top two, and then I chose the bottom two. One of them, you always end up having to use twice, no matter what, in the system with 3 variables like this. And so I chose the top two, but if you wanted to, for some reason, choose the top one and the bottom one, you could. You could have combined those and then eliminated the C's again, or the A's or B's, whatever you're eliminating. But we've chosen the C's. So right now, again, I have the same problem. I have a 1C and a 1C. That's not going to eliminate if I add these together. So I'm going to have to make that a negative 1C right there by just, all I'm doing is really changing the signs there. And now I can combine these with addition. I am changing the bottom one because usually it's easier to see that it'd be subtraction right here with this stuff. But you could, if you wanted to say, okay, keep that 29 positive and the 16a positive and the 4 positive and the 1c positive, you could. And then you could have made this -5 and -1 and -1 and -1. You could have done that, yeah, you could have. And that's the beauty of elimination with systems with 3 variables. There's so many directions you can go, and you can have so much fun doing it. All right, so let's eliminate then. So 5, I would just say 5 minus 29. There's going to be -24, which is going to equal 1 minus 16a's would be -15a's. And then 1b minus 4b's would be -3b's. And then again, the c's have eliminated as planned. So we now have 2 equations, and that gives us a system with 2 variables. So let's write these again. Let's take these and separate them. These problems, they are long, okay? So you have to be careful. If I've made a mistake right now, it's going to really do a number on us later on. So we got to be careful. So -15a and then a -3b. Oh, this is great because as it is right now with the b's, hey, look, the coefficients are the same, -3 and -3. All I got to do is change some signs, and they will eliminate as well. So that's what I'm going to do.
It's 2. So it's negative.
Okay, so I'm going to change those signs. Again, I like to change the bottom ones. You're welcome to change the top ones, but that'd be a +24, +15a, and then a +3b. Maybe I should change the top ones. It doesn't matter. But now this will give me an equation with 1 variable because now the b's will eliminate, right? We got the 3b's, and it was showing plus, but -3b's plus 3b's zeroes out or eliminates itself. So 12 plus 24, that'd be 36 equals 3a's plus 15a's is 18a's. Holy smokes, I wish someone had told me earlier, but the answer here is A is 2. So So I'm gonna divide both sides by 2. A, as it turns out, is 2. At least if we've done all the stuff correctly to this point. If I've made a mistake, this 2 could be off. It could be off, right? But hopefully we've done this correctly. Now A is 2, and we have so many equations to work with. We have 1, 2, 3, 4, 5 equations that we can work with to solve for either B or C. I know from these 2 equations that it's going to be easier to solve for B because now I have an A value to plug in. And it doesn't matter which one that I choose. I choose the one on the left because it has smaller values. So I'm going to take that 12 equals 3A minus 3B. But now we're pretty sure that the A value is 2. So I go in here, I say A, I'm going to replace that with 2, the 2 that we found already. And so I just need to solve this equation for B. So 3 times 2 there is 6, so 12 equals 6 minus 3B. And then I'd use some principles of equality to solve, so minus 6 from both sides. So I get 6 equals, this being negative 3B. Sorry, that's kind of small. But now I can divide both sides by the coefficient of negative 3, and B equals negative 2. Okay, so we got 2 and negative 2. All we need now is C. By the way, if this is correct, you can replace the A there with negative 2, and if you do, you should get a B value that is also, I said replace A with 2, B would be negative 2. Do some analysis here. Make things easy for you, but you don't have to because the calculator really is going to do a lot of the work. We need to now solve for C. We have this system of equations that from the beginning. Neither of these 2 equations are going to help you solve for C. They help to solve for B, they help us to solve for A, but they don't have a C in there to solve. So you got to go back to the original system and use one of these to solve. I am going to choose the middle one because I don't see any coefficients for A or B, so I don't have to multiply by anything. That's going to make that very pretty. So let's take a look. Okay, so I've got, 5.
Please, Jorge, that's not how.
5 equals, the A value that it gave us was 2. Now, I don't need that coefficient either. The B value that we found was negative 2, so it'd be minus 2. And then this would be plus C. Well, as it turns out, when you, let me see what I'm going to do this in green. When you combine those 2 minus 2 right there, it just really zeroes out. And you're left with, well, C equals 5. Now, if, let's say that you didn't choose that equation. Let's say you chose this one right here. Then you would have had 4 times 2 minus 2 times negative 2 plus C. And then you would have solved this for C. You would have still gotten 5. Same with this one right here. So as it turns out, it looks like that we've solved this correctly. If you were to replace A, B, and C into all 3 of these, you'd get true statements all around. And then everyone would be very happy. But let's go back to the quadratic, okay, because it wanted the actual quadratic equation. So it's y equals a times x squared plus b times x plus c. And in fact, it won't even be plus right there. But the a value that we found down there at the bottom, a was 2, so I've got 2x squared. The b value down here is negative 2, so that'd be, I'm just going to show it as minus 2x. And then the c value that we found was positive 5. And that's the equation right there. That's the quadratic equation.